What if your electricity came from a solar farm in space, a place where sunlight is available almost all the time? And imagine if that power is beamed to Earth like Wi Fi. This isn't fiction anymore. In this video, we will cover space based solar power, which does sound like sci fi, but advances in lightweight arrays, in space demos, and plunging launch costs are making it plausible. So let's look at how it works. A satellite in geostationary orbit spreads out huge photovoltaic sheets, converts sunlight to microwaves, and beams them to a receiving antenna on the ground. The antenna turns those radio waves back into electricity and feeds the grid. It has to be mentioned that a satellite in the geostationary orbit can see the sun almost constantly. It can receive solar power that is not attenuated by the atmosphere as we receive on the ground. And this means 1350 watt per square meter of power as opposed to just 1000 watt per meter square peak power. The only exception are two short equinox seasons when the Earth blocks the sun for up to 72 minutes per night, lasting just a few weeks. With batteries bridging that gap, you get power that's available for over 95% time of the year. This means essentially 24/7 solar power. On the ground, the receiving antenna is several kilometers across but made of open mesh. The power density at the edges is comparable to sunlight, safe for people, and you can even farm underneath. For additional safety, these antennas, or more specifically rectennas, can be placed offshore. So, why is space solar looking more feasible now? Firstly, because of real in orbit demonstrations. In 2023, Caltech's Space Solar Power demonstrator wirelessly transmitted power in space and even reported detectable energy beamed to Earth. The second reason is the new deployable solar arrays. There are now origami inspired designs like the Miura Fold and rollout systems like the NASA's ROSA that can pack into tiny volumes and then unfurl to tens of kilowatts per wing, and that reduces the mass and stored size by huge margins compared to rigid solar panels. There is a company called Space Power that is even contemplating to build a spiral array in space using autonomous robots. And the third enabler is the launch costs. The space shuttle used to cost around $54,000 per kilogram to deliver payload to orbit. Today, the Falcon 9 gets you there for less than $3,000 per kilogram. For Sun synchronous orbit using rideshare slots, the cost is advertised at about 6,500 per kilogram, and that's more than a 20-fold drop in costs. There is one practical question that is often asked. Do solar panels in space need a glass cover? The answer is yes. Thin fused silica glass cover protects the cell from ultraviolet light, radiation, and micrometeoroid damage, extending its life from few years to decades. This cover, though, is just 100 microns thick, thus keeping the panels flexible. It adds to the mass, but without it, the efficiency falls off too quickly. So, to summarize, the first generation system might be modular with many lightweight panels launched and robotically assembled into kilometer scale structure in the orbit. Power would be beamed down at microwave frequencies to a rectenna which would be a few kilometers wide. The rectenna can be kept floating or with land still usable underneath. The challenges remain: massive structure, precision beam steering, safe certification, and competing with even cheaper terrestrial renewables. But every ingredient, that is, the lightweight arrays, wireless power, and cheaper launches, is improving fast. Space solar won't replace wind and ground solar, but it could complement them with near continuous power. If the pieces keep coming together, the next decade could be when the sun finally becomes the true 24/7 energy source by going to space first. Do let me know what you think about this technology. Thanks for your time and attention.